So today we talk about trig derivatives, but before we do that, let's quick review the power rule.
Oh, I don't know we did last week.
Yes,
Yay.
I did throw a little new twist in here. What's the derivative of the first part?
6x squared.
6x squared. What about the second part?
It's 7. Well,
This is the same as negative 3x to the 1/2.
so so
Negative 3/2. So I multiplied
oh,
in front by
yeah,
1/2, and I subtracted 1 from the exponent.
right.
To simplify y prime, I would probably put it back like that. 1/2 becomes a square root, negative moves to the denominator. See how that square root wasn't really harder. You just had to change it first. We're going to do that. There's going to be several things. If you have another one, 1 over x to the fourth, I would change to x to the negative fourth. Now apply the power rule.
Oh, negative.
Negative 5. Subtract 1, don't go closer to 0. Okay. And then we had the product rule and the quotient rule. The derivative of two things multiplied together. First times derivative of second plus second times derivative of first. The quotient rule, oops, was that, correct? You guys have your math Bible handy? Yeah, because you're going to need the calculus sheet a lot. And what I'm about to show you is just a whole bunch of derivative rules that people have proven over the years. That just shrunk it massively, but
The power of x is.
e to the x, yes. Yes, there's some easy ones that we're not going to be doing directly today. Welcome to the world's easiest derivative. I told you E would be nice when you got to calculus. Natural log, so log base E is just 1 over x. It's not awful. I believe the LNA is on the bottom for that one. Log base A of x. So anytime you're doing one of these, you're just going to look at your sheet and go, what's the rule? There's a video posted of me proving that using the definition. I believe this is also proven in that video, but you don't have to use the definition for this one. This one, tangent is sine over cosine, correct?
Yeah.
If you use the quotient rule with sine over cosine, you can get secant squared. And cotangent being cosine over sine, you get the same thing. That can also be done with the quotient rule with just 1 over cosine. Okay. There's all of those derivatives. Now you just have to use them. Okay. I don't have room to leave them all on here, but you have them all right in front of you in your packet. So, using them. And remember how I told you to practice the product rule? That even though you could probably multiply it out and sometimes it was simpler on the ones. This I can't multiply out, can I? It is multiplied. So I'm using a product rule. I'm going to do separated as u and v. The derivative of u is what?
2x.
2x. If I do the derivative of first, it doesn't really matter the order you do it in. I a lot of times will do derivative of first times second plus second or first times derivative of second. What's the derivative of sine? And there's our derivative. It didn't get simpler like nice polynomials do, unfortunately. I'm just going to put these in colors right away. So here my derivative. Bottom times derivative of top. What's the derivative of the top here? Negative sine x. This is big enough, isn't it? Minus cosine x times derivative of the bottom. What's the derivative of the 1 minus sine x?
And it's cosine.
Minus cosine x.
They do it before. So
So now I'm going to distribute sine x of negative sine x plus sine squared x plus cosine squared x. Oh, I forgot the squared there. What's sine squared plus cosine squared?
uh,
Other backwards.
that's what I was scared of.
It's on the trig identity page.
I don't know. I don't like being bad. It's one.
It's 1. So negative sine x plus 1 is the same as 1 minus sine x, isn't it?
Yes.
I'll do that in a different color. So that nice, lovely derivative is just 1 over 1 minus sine x.
Mm.
Yes. Quite a bit of work to get there, wasn't it?
Mm.
Just be glad that you're not doing this by definition of derivative. Because I would have needed 12 screens that long to get there, I think. I don't know. Never really tried to do it. Motion on an oscillating spring. So I believe we talked briefly about position. And we will use S for position in this course. Do you remember how velocity is related to position?
Mm.
The change in position over time, correct? Which that's a rate of change. That's a derivative. Acceleration is a rate of change of what? Velocity.
Makes sense.
Yes, yeah, everything is connected. Yes, it is a Monday. The jerk is the rate of change of acceleration. And then if you want to get to the fourth, fifth, and sixth derivative, I think it's the snap, the crackle, and the pop. Nerds have too much fun sometimes.
I think also have right.
I mean, it's not really hard. You just keep taking derivatives. With a trig function, it would be hard. With a polynomial, it's like a big deal. Who cares?
There's a lot of work.
It's a lot of work. So, do you guys have your book in front of you? Grab a book. I want you to see the illustrations here.
What page?
Page 137. So we have an oscillating spring, or 136. Look at the oscillating springs in the bottom corner. Okay. We've got its rest position. Once it starts oscillating, it goes down and then up. That kind of makes sense. It's a fairly logical thing. And it's predicted by this position function. How do I take the derivative of this to get the velocity function? Hmm. I don't need a product rule because 5 is a constant. What's the derivative of cosine t?
Maybe it was, oh.
That's not too bad, is it?
Oh,
What's the acceleration?
it's the derivative of sine machine.
Well, what's the derivative of sine?
Cos-
Cosine. So it's just negative cosine. So now I just put the negative with the 5. That's not too bad, is it? Yeah, you can. Like on one where the last one where you've got product rules and quotient rules and stuff, it gets pretty ugly. But this, no, who cares? Look at how the original function in blue on 137 is related to the velocity function. The blue is the original, the velocity's in red. Notice that they're just offset by a phase shift. That is oscillating motion. What is being modeled there is what's called simple harmonic motion. Assuming that nothing affects its motion, it just keeps oscillating back and forth and never shrinks. Can you think of any other examples of simple harmonic motion?
Pendulum.
The pendulum, yeah, that's a good one. A spinning wheel is actually one too. Keeps coming back to the same position.
Right.
Okay, now we're gonna find the jerk.
Maybe 5 sine.
So -5 times negative sine, right? Which is +5 sine t. Not so bad, huh?
I guess.
Like, these aren't that bad. You got to keep that sheet in front of you because you don't have them memorized yet. That's fine. So now we're going to take this function
Uh,
and we are going to find the tangent and the normal to the graph at x equals 2. First thing I want to find is f of 2. Coleman, you got a calculator? Make sure this is in radian mode for this.
Well, big 5 minutes, but we don't really time.
Okay. Well, let's see. Hopefully mine won't take 5 minutes to boot. It didn't. Just have to switch modes.
I think it's because I don't use it over the weekend. I don't use mine over the weekend. Oh, I don't know.
It just depends on how long it's been off for. Negative 1.09. So I've got this for my coordinates. How do I get my derivative?
Bullshit rule.
Quotient rule. Bottom times derivative of top. Derivative of tangent is secant squared. Minus top. Oh. Minus top times derivative of bottom. Derivative of bottom is 1. Now I gotta do f prime of 2. And the beautiful thing about your Inspire is it actually has a secant button. When you enter it, you must do secant 2 close parentheses, then the squared. You cannot put the squared in where we write it for the shorthand notation. You guys remember that from last year?
2 secant.
So you do 2 and please try this if your calculator is booted.
Why does it have to take slop?
Yours is an older version.
There we go.
Just want to make sure we're all going to get the same answer here.
Five minutes. Sure.
You got a different answer?
You're gonna be out of degrees.
It's like, mine's right. And that's what the book says.
You know, I got the same. If I switch to pretty left.
Let's go up to where it says DEG and click. My calculator locked on me on Friday and this mouse thing didn't work.
Oh,
I restarted it and it worked.
okay, that's good.
I just went off on. And it didn't like do a full reboot, but it did enough apparently. I got 3.43.
Yeah. We can get once, not 5 times. So you can also over to me. Oops. Studies. 5.7.
Once in a while they act up. So the tangent line, y plus 1.09 equals 3.43 x minus 2. If you'd like, you can put it in slope-intercept form. The normal line. Done. Not so bad, huh? Okay, last thing we're gonna do is take a trig second derivative. What's the derivative?
DK x times 2.
No, oops, that's the first derivative. Second. Now to do the second derivative, I must do the product rule. Derivative of first times second. This is probably one where I should do colors.
Yeah, better.
Derivative of first times second plus first times derivative of second. And yes, you do need to simplify this. Doesn't simplify a ton, but and there you have it. That wasn't so bad, was it? Okay. That's it for today.
Making extra some bird.
Mhm.